In today's podcast, I'd like to talk about filters. Filters is a way of looking at the part of a complicated signal that only the part that you want to look at, whether that has a low frequency, medium frequency, or high frequency. So take a look at this signal and see how many frequencies you see in here. I think you should see three. There should be one with a long period, the low frequency wave on this order. One that's sort of the 5,000 hertz, that's a medium length period, and one that this small period is the highest frequency, 20,000 hertz. And so this wave is some combination of those three signals. And so you might imagine that, hey, I only want to look at one of those frequencies. And so that's the idea of the filter. The filter lets us put in this input signal and either pick out the low frequency 500 hertz, the mid frequency 5,000 hertz, or the high frequency 20,000 hertz. And the basic idea is we're going to put some input in, this complicated input on the left, and we're going to take out whatever frequency it is that we want. So how do we do that? Well, first let's look at the low pass filter. Low pass filter consists of a resistor and a capacitor in series, and we take the output across the capacitor. So our input is whatever our signal is. In this case, it's going to be the signal generator, and the output we're going to measure across the capacitor. And so you can think about the capacitor at high frequencies. This capacitance, the impedance of the capacitor is going to be very small compared to the resistance, and so there'll be very little voltage across there. So at high frequencies, we won't get any signal across the capacitor. But at low frequencies, the impedance of this capacitor is actually very high, larger than the resistor, and so most of this input signal will be across the capacitor. So that's the basic idea. Now we can go through and calculate that as well, right? And we can calculate the gain, which is just a V out over V in, which is going to be the voltage across the capacitor over the voltage of the signal generator. Well, we can write those down in terms of the current. The voltage across the capacitor is just the current times the impedance of the capacitor, and the signal generator is just the current throughout the circuit times the total impedance in that circuit. And so if you do that, and you substitute in the impedance for the capacitor and the resistor, then you get the following relationship, right? Which says what we want. At high frequency, this is dominated by this term. It goes to 0. At low frequency, this term disappears, and the gain is just 1. Okay, and so we can also write it in this form, where we have a real part and an imaginary part as well. So fine, we found the gain. Now we can find, well, what's the magnitude of the gain? That's just going to be the complex constant of the gain times the gain, take the square root, right? And so if you do that with the function we just found above, you get the following relationship, the square root of 1 over 1 plus omega RC squared. And so this RC, right, just depends on the components that you're using, and so really is a function of the circuit that you built. Like, it's a characteristic frequency of the circuit, and it turns out we can define a frequency omega RC that's just 1 over RC, and if we do that, we can rewrite this gain equation in this way, and you can kind of see that, hey, the gain only depends on the frequency that of the signal generator, and it sort of depends on some characteristics of your circuit. What's R, what's C. And it also illustrates that the gain is dimensionless, right? It's because we're going to take the gain times the input voltage is going to give us the output voltage, so it shouldn't have any units. And so we can look at the plot down here and see that at low frequency the gain is 1. All the input signal will be across the capacitor, and we'll get it as the output. And at high frequency there's almost none. And so in between, well, it's something in between. And it turns out that this point is omega 3 dB, which we defined in the last podcast was really where the power out is equal half the power in. But in that case, the gain was equal to 1 over the square root of 2. So in this case, omega RC turns out to actually be the 3 dB point. And so what's important about that is that's the point where we say this filter, that's the cutoff frequency. So for this low pass filter, if you have frequencies that are lower than the 3 dB, then that means the signal is going to get through. And if you have signals a higher frequency than the 3 dB point, then they won't get through. Now obviously that's not entirely true. especially if you're close to the 3 dB point, but certainly it's approximately true, and you should just realize that it is an approximation. At the same time, we can calculate the phase, and we can go through the arctangent of the imaginary part over the real part, which we can just pull from this equation up here, and we can find that the phase angle is just the inverse tangent of minus omega over omega RC. Right, and the important point there, I plotted that below, is that when at low frequencies, the phase constant is zero. Essentially, the output voltage is in phase with the input voltage, and the farther away you go, or the higher above the 3 dB point that you are, down in this region, then your phase differs, right? And to where at really high frequencies, you're just out of phase. Okay, so that's the low pass filter. Again, this passes low frequency signals. So if you put a signal in there, what you'll get out are the low frequency components. So the next one is the high pass filter. We can go through the same sort of mathematics and get this relationship, but the thing to notice is that this circuit is exactly the same as the last. The difference is we're taking the output across the resistor. So remember what we said before. At high frequencies, this capacitor, the impedance of the capacitor is essentially zero. So all the input voltage is across the resistor. And so that's what we want. That's a high pass. So all this, we get the signal at high frequencies, but at low frequencies, the impedance of the capacitor is really big, and so we get almost nothing across the resistor. Okay, so that's what we mean by a high pass filter. The signals, when the frequency is high, make it through our filter. So again, we go through, we find the gain, we make our substitutions, and we find this relationship. Or we can write it as a real and an imaginary part over here. So that's our gain. We can find the magnitude of the gain and make the same, it turns out, simplification, or definition, omega RC, right? The characteristic frequency of the circuit is equal to 1 over RC. So this is exactly the same as a low pass filter. Not surprisingly, it's the same circuit, right? Just we're taking the output across a different component. And so the characteristics of the circuit are exactly the same, only in this case, it's omega RC over omega. So we get at low frequencies, this becomes very big, and so the gain is approximately 0. At high frequencies, this term essentially goes to 0, and the gain is just 1, which is what we want from a high pass filter. And so again, this graph shows that relationship. At high frequencies, the gain is 1. At low frequencies, the gain is essentially 0. What low, high compared to what? It's really that 3 dB point, or omega RC, which is somewhere right here. So that's when we're at frequencies higher, the signal passes. When we're at frequencies lower, it doesn't. And again, we can calculate the phase, imaginary part over the real part, arctangent, and we get a function that looks similar but opposite, that essentially the signal is out of phase at low frequency and in phase at a high frequency.